Then I've got a quick intro slide here for Home. So he has earned his bachelor's from Michigan Technological University, which I believe is in Houghton, Michigan. I've got some friends from up in those parts when I used to live in Michigan, so that was kind of a pleasant little surprise to see on your CV there.
Yeah.
Home then went on to earn his master's and PhD from Purdue University. All of those degrees were in electrical and computer engineering. Home did postdoctoral fellowships with Peter Albersheim and Jim Prestegard in structure determination of carbohydrates and computational methods of protein structure determination. Home is now a professor at the University of South Carolina. He's in the departments of computer science and engineering, and I believe a dual appointment with biomedical engineering as well. What caught my eye on his appointment there, he's also an associate infrastructure director in the area of visualization. That was something I had a hard time kind of tracking down some more info on, but I know in the biomedical sciences, we're always scrambling to get better visualization tools for very complex data sets that we work on. And I think that kind of shows in a lot of the software that you've developed and designed. So that's kind of an interesting thread there to your background. Also in the work that you've done, I've put one graphic here on the slide. I think in your structured determination work in particular, to be relevant today, you really write about quite a bit and kind of emphasize in your design the ability to balance computational approaches and experimental approaches. And I think that's really kind of essential to this area of work. And I just wanted to throw a graphic in there to plug that. And with that, I think I'll turn things over to Home. And thank you again for joining us. And we really look forward to your presentations today on Redcraft and everything you've done for the NMR community. So thanks a lot.
Thank you, Adam. Thank you for that introduction. My pleasure. I'm happy to give you an introduction and maybe a summary of the Redcraft program. And so what I want to do to be a little bit more complete, Redcraft is something that we have produced for calculation of structures, specifically proteins from residual dipolar couplings. But where it has extended that becomes kind of unique and potentially interesting is how we can also concurrently treat structure and dynamics. And in all of my work and my publications, I try to stress the fact that in particular, when you're trying to study characterized structure of proteins, you cannot do the two separately. You cannot treat structure and dynamics separately. You have to be concurrently aware that both could coexist, and you have to treat them both. So our work kind of extends into characterization of structure and dynamics of proteins. So getting through today's work, what I like to do is first spend maybe 15-20 minutes to briefly describe the approach taken by Redcraft, because it is traditionally very different than how, for example, you fold proteins, let's say in Explorer, in Cyana, or any of the other programs. So it's substantially different, it's completely a different approach. So I kind of want to go over the general how it's done, how it's performing its structure calculation. I have maybe 10 slides that I'd like to go through it. And from there, what I want to do is just jump back on a hands-on version of it. And I am happy to follow your lead and your requests. I like to do things the way that it would make sense most to you. If you do not have a particular request, then I'm going to go the default route of I'm going to demonstrate the app with you guys watching to go through one particular analysis, talk about the features, what features it has when you turn them on, when you're not, and what is the function of each feature. And from there, maybe the latter part of the workshop, if you guys are interested, we can work on folding protein, I believe either, I don't know what I uploaded, either GB13 or it's ubiquitin is one of the two. I don't remember which one it is. So we can take a look at that. But I like to start everything by just an overview and followed by working with simulated data. I know people, when it comes to experimental NMR spectroscopy, people just don't like to work with simulated data at all. Whereas from my world, which is starting from the computational world, is the absolute essential way to approach it, because I can control how much error there is, I can control how much missing data there is, and really study the behavior of an approach with respect to sensitivity to error, sensitivity to missing data. And from there, then we can jump into experimental data. So I'm going to start my demonstration with synthetic data, and it's complete. It's kind of, it has only limited amount of error, but to demonstrate the features of the app, and then jump onto experimental data that we have downloaded and formatted from VMRB. But let me, if you guys do not mind, if I can ask whether you guys want to follow what I am doing hands-on, in which case I'm going to take a different strategy, or you want to sit back, watch what I'm doing, and essentially then only one round of, maybe we can all do protein folding, maybe we can jump onto experimental data, not synthetic data, and we can do that at the end. Do you folks have a special preference?
If we could try doing a more hands-on approach towards the end, if that works.
Okay, that sounds good. That works for me. And of course, at any given time, you guys can say, stop, I want to test this particular part myself. I do realize that in my years of working with residual dipolar couplings and some of the claims that I have made, it has actually, there may be a lot of skepticism out there, but I highly welcome a skeptic conversation rather than a person who is already on board. So if you have any concerns, any questions, you want to play the devil's advocate, please jump out and say so. It helps us to improve our approach. But I suspect I'm going to be able to anticipate some of them, and I'm going to try to address them as we go along. So let me start by presenting an overview of what Redcraft does. So I hope, can you see my screen? No, I'm not sharing my screen yet. Hold on. Let me share my screen. And can you see my screen at this point?
Yes, looks good.
And here is my presentations up. All right. So today I'm going to focus on how we characterize protein structures from residual dipolar couplings, but our work extends into dynamics. And if you have any interest at the end of this workshop to see how our work extends to treatment of dynamics, characterization of dynamics, please let us know. I'm more than happy to hold another 2-hour session to work on dynamics. And we are always looking for collaborators. We are always looking for people with data to analyze. We are always looking for partners to write grants with. So if there is any potential for partnership, please keep me informed. So I'm not sure why the bottom says UGA CCRC, must have been for something from the past. So disregard that. A quick overview of how structure calculation is traditionally done in the NMR and computational communities. So typically you require 15 to 20 NOEs per residue. You collect primarily your NOE-based structure calculation. So you collect NOEs and a variety of other data types that come along with it. Talos, for example, constraints, you may have some sort of a J coupling restraints, and so on and so forth. You collect all that information and you throw it at a program such as, for example, I'm going to say Explore NIH. And Explore NIH or any of the other variations that exist out there, you throw all the data and those computational facilities try to reduce a potential energy that is a sum of empirical and effective terms. And the effective terms is essentially all the experimental data that go in there. And you have terms such as you take the distance between the two pair of atoms from the structure that you have compared to the NOE distances. And from there, the point is to minimize that while also introducing imperial terms to make sure that the bond distances are not violated in basic geometries of the peptide plane, and atomic bonds and covalent bonds are not violated. So empirical terms plus the effective terms, you throw them all in there, and then you deploy some mix of Monte Carlo or gradient descent approach in trying to minimize the structure to satisfy all your constraints. And from there, you perform structure calculation. And along the line, you start with the extended structure. So things are a little bit jittery. So you start with an extended structure where everything is kind of set at the dihedral angles of -180, -180. And as the process of folding of the protein continues, then your protein folds into its globular format and hopefully into its final structure. Some example of what it may look like. So if we were to put a contrast between what NOEs do versus what RDCs do, and our RDCs in particular approach with our RedCraft, I'm going to do this. Some of it is required background information that I'm not putting in here. You will see it as part of the demonstration. But what the concern that has come up in here, my point in producing this is not to indicate that RDCs are better than NOEs. We should give up NOEs and purely shift into RDCs. That is not at all the intention. The plan, my personal approach is that we need to understand each source of data individually on its own, to understand what are its pros and cons. So that way, when you're approaching structure calculation, you can, in a more informed way, mix and match your data. So for what you will see, I'm hoping to be able to actually go through some of the demonstrations today. We can fold proteins with just 2 RDCs per residue. So if the contrast is NOEs, you need to have 15 NOEs to fold proteins. In RDCs could be a potentially cheaper, faster way of doing this. And some of this, again, is not going to make sense at this point, but you will see as we go along. Traditional approach is to just start the entire protein as a whole. So if you have a protein that's, let's say, 100 residues long, you just right off the bat, you're working in a very complex landscape of variables of search dimensionality is already at its maximum. As you will see, RedCraft tries to calculate the structure of a protein for residues 1 and 2 first, and then it appends residue 3, and it manipulates its geometries. Then it incrementally increases the size of the fragment 1 residue at a time. Because of this increase, the gradual increase in the protein size, right off the bat when it engages, the protein size is very small. It's just 2 residues, 3 residues, 4 residues. And it gradually increases to be a full-size protein. So the complexity of the protein energy landscape is just gradually increased, not just as one big, right off the bat. It performs some sort of a combinatorial and sort of exhaustive approach. So what it does, it takes residue 1 and residue 2. You'll see this in the next slides. It's fairly robust to missing data, and its operation is entirely in the rotamer space. This is a very critical thing to actually keep in mind. So when you are conventionally, when you fold proteins, you are in a Cartesian space when every atom can go anywhere in space. So atoms are moving around independently of each other. When they're moved around, then you evaluate a potential energy. And if there's a violation in bond distances, bond geometries, then it will be reflected and it will be corrected. RedCraft operates entirely in the rotamer space. That means it manipulates the structure of the protein by purely manipulating phi and psi, the backbone torsion angles of the protein. For that reason, the peptide geometries are never violated. So there is no point in including bond term, angle term, dihedrals, and improper. Those terms will never be violated, and they're always optimally in place. The only things that you need to put in place is van der Waal electrostatic and residual dipolar coupling terms. So your energy term is simplified, your calculations are simplified, many things are simplified. And at this point, a critic would stop and say, hey, look, yeah, you're correct, this is simplified, but in return, what you gave up is we know, for example, omega angles are not always stuck to 180. They vary by about plus minus 10 degrees in an acceptable structure. And sometimes there's a cis to trans conversion, for example, prolines, that will severely violate that. And there are a number of things we have in place. First, there are ways that you can modify this, but the general argument here is that if you find a reasonably good approximation of your structure, then you can take that structure as a starting point for minimization in the traditional Explorer and other platforms. So Redcraft by itself may not be able to give you high resolution structure, although I will show you today that it does. But if you're going to argue that, you know, omega angles need to be changed, so at that point, the answer would be yes, do Redcraft first, then do Explore NIH, at which point everything varies and you get a really good structure at the end. So I'm going to skip over RDCs, what they are, what they do. And I'm just going to jump to this particular slide that I think is critical in understanding the effectiveness of RDCs versus NOEs. So in this exercise, what we have done, we have grabbed one structure, and I don't remember which one it is, and it is not that important. From this structure, altering its phi and psi dihedrals, we have generated 5,000 derivative structures, and these derivative structures exhibit as much as 25 angstrom deviation from the actual structure. And all of these 5,000 structures have been subjected to fitness to NOE constraints or RDC constraints that were experimentally collected, and they were available at BMRB. And NOE is shown in kind of pinkish in the bottom, and RDC fitness is shown in blue on top. And you can see the complementarity of these two data sets. You can see that NOEs, basically what this says is NOE, by the way, and the scores of fitness to the data are normalized to fit between 0 and 1 in order to make it comparable between NOEs and RDCs. And you can see that NOEs essentially, okay, one more addition to this, when we fold proteins, we really only have fitness to our data. So the only access that we have is a score that comes out of our products, whether it's Redcraft or Explore NIH, that says your fitness to the data is 0.2. And the question that we always answer, we try to ask and answer is that, what kind of RMSD, backbone RMSD variation does that particular score correspond to? So if you phrase that question from that perspective, you can see that high fitness to the data, that means poor fitness to the data. The RDC corresponds to a really large variation of the backbone RMSD. So in this particular instance goes anywhere from about 3 angstroms to approximately 20 angstrom variation. Whereas NOEs fits into a tighter one. So it's somewhere between, let's say, 16, 17 to about 24, 25. So it basically indicates that NOEs are better, have a tighter association between fitness and the backbone RMSD. As the structure folds and you get closer and closer to fitness of the data, you fit your experimental data better, then you see a different picture. So at this point, for example, if your fitness, normalized fitness was at 0.2, the RDC variation, RDC-based structure variation would correspond to anywhere between 2 angstrom to about 5 angstrom, whereas the NOE-based structure would go from about 10 to about 16, 17. And really the differential point becomes at the very limits of our fitness is what happens when your fitness goes really, really low to 0.05 and to when you really approach to structure that fits well to your experimental data. And you can see that the ambiguity in the structural, the suitability of the structural accuracy limits itself to about anywhere from 1 to 2, 3 angstrom, whereas NOE remains very insensitive. And you can use this to answer a number of questions or anomalous observations that have been stated in the community, including why is, sometimes X-ray structures kind of seem to vary quite a bit with NOEs. Why does NOE-based structures kind of exhibit X-ray structures fit RDC structures better than NOEs. So this can possibly be used for something like that. Let me stop at this point and see if there are any questions to basically get everybody maybe a little bit more relaxed about asking questions. Are there any questions at this point? I haven't really described anything about Redcraft yet.
Just a question about this chart.
Yes.
If you were to combine RDCs and NOEs like you suggested in one of your previous slides,
Right.
would you, what effect would it have on the normalized score?
Yes, very good question. It's something that I believe the community have actually wrestled with. What is the appropriate way of combining RDC and NOE data? And let me inject in there my own objective in there is that the only way you can answer that properly is by looking at each one of these data sources individually and then combine them appropriately. But I am actually going to show you a figure relates to that when the two are combined. So if there are no more questions about this, I'm going to go to the next slide. Actually, the next two slides that are going to address this particular question and another thing that I want you to be aware of. If there are no questions, okay, so what I want you to do is to be aware of this particular phenomenon. It is possible for you to start from a structure, and this is not just confined to RDCs, this is RDCs, NMR, and all other data sources. But just be aware, you can start from a structure, let's see the one that my pointer is pointing to. That particular is your starting point of investigation, and that particular protein is 3 angstroms away, but exhibits a really poor fitness to the RDC data. And you engage in your process of minimization. And as the process of minimization continues, you are only aware of this score. And this score, it is possible that your exploration of the conformational space leads you to this particular point where it's a substantial improvement in the fitness to the experimental data from 0.9 to 0.5. But in reality, behind the scene, what we do not know is that your structural fitness kind of decayed. It went from 3 angstrom now to 10 angstrom. But the point is that although in a short-term minimization of your objective function may reduce the quality of your structure, if you insist on discovery of the global optimal point, you eventually rework your way down this funneling effect in order to find your way, hopefully, if your global optimization technique is working, into the optimal structure, which basically means now you're going to operate down here, and your structural ambiguity is going to be about 1 or 2 angstrom. The same thing with NOE. You start up here, you do some sort of a walk across this entire space, and if you insist on your optimal search mechanism to operate, then you will eventually find your way to the minimal structure, but there is more ambiguity from the perspective of NOE than it is from RDCs. With NOE, I wouldn't be surprised if at some point we establish that really the NOE's resolution of structure is about 3 angstrom, I would argue, based on this phenomenon. Now, of course, the question is, we have repeated this exercise for a number of structures. The pattern remains fixed, but still is 4 or 5 structures that we have looked at. And the question is whether that's generalizable to all structures or not. Before addressing the question with Redcraft, let me address the question that was asked. So if you combine the two, this is what you will see. So if you combine residual dipolar couplings with NOEs, you will get this kind of like green pattern in the middle. And it depends on what you see here now. So it depends on who you are. Is the cup half full or half empty? You can argue that you have exactly managed to achieve a compromise between the two, where you're not as insensitive as RDCs when you're far away, and you are not as insensitive as NOEs when you're close to optimal points. So it's kind of like a mix of two, and it seems to have the benefit of both. But my argument is that we should be able to do even better than this. My argument is that at this point, so when you're operating at low region here, you are not taking advantage of the full benefits of RDC in that structural anomaly or ambiguity is broader than what RDC allows. Whereas if one was to approach this in a different way, when you start your structural calculations from an extended structure from an NOE-based investigation to get somewhere down here, and at this point shift everything, rely primarily on RDCs, then you can basically go RDC-based and you can go down. So not mix them, but use them initially and switch to the other one. Or if you want to think of it, start with a bigger weight on NOE and gradually shift it to bigger weight on RDC and have a dynamic approach that will then combine everything together. Is that clear what I'm basically proposing here?
Yeah. Is there a particular reason why one should begin with an NOE?
Why one should what?
Why one should begin a structural calculation with NOEs rather than starting with RDCs?
From this particular graph, if the plan is to start with an extended structure, okay, if that's the approach, the general approach that the community takes, an extended approach, if you were to do a best fit to this data would go, basically you can think of the middle part and you would go like this. The NOE-based curve would have a steeper derivative and therefore sensitivity between fitness to RDC and backbone RMSD. So NOE would be more effective in leading you into a more fit structure. So it would be a better way of engaging from NOEs to go from 25 angstrom to, let's say, to 15 and 10 angstrom. And at this point, NOE loses sensitivity and RDC then gains sensitivity. So then one would start with NOE to do a more rapid approach towards converging to your structure. And then you would switch to RDC and RDC would have the higher sensitivity and you would then have a much faster and direct governance of being guided towards your final structure. And this, by the way, is if you start with an extended structure, stick it in Explorer and say, here are my RDCs, you essentially are gonna observe some sort of a random walk and you're never gonna get the right structure, which is why the traditional approach of starting with an extended structure, minimizing in Explorer will not work. You need to have new approaches, either start with NOE, end with RDC, or just start with RDC and just have a different approach. Now, one more thing, so the approach of start with NOE, switch to RDCs really inflates the cost of structure calculation by NMR spectroscopy because you have to collect all the data that you want, that you need. So which is NOE, all the prerequisites for NOE assignment of resonances, and then RDCs and all of its prerequisites of sample alignment and so on and so forth. So it's costly. Whereas the decision that we made, and this is rooted in the world of structural genomics, in order to reduce the cost, reduce the number of experiments, why don't we focus on structure calculation of backbone from residual dipolar couplings alone and come up with a new methodology that will fold proteins just based on RDCs, which is the motivation that we had. So if there are no questions at this point, I'm going to switch to what RedCraft does. In principle, it's very simple, I feel, but
Home, there was one question from Maheen. He's raised his hand in the sidebar there.
I'm sorry, I don't, sidebar for some reason just shows a limited number of people. So
yeah, when you're presenting and sharing screen, sometimes you can miss out on some of the Zoom tools.
yeah, so
I'll keep an eye on it for you.
Sorry. So what was the question? I don't see the question, or does anybody want to ask the question?
Maheen, we can't really hear you. I see that you've unmuted yourself, but I'm not hearing the audio.
I barely hear you.
If you'd like to type your question in the chat window, we might be able to proceed with that. Otherwise, maybe we can come back to it at the end of this session.
Yeah, it might be also a microphone setting on your end, since neither Adam or I can hear you. So it's probably a microphone sensitivity issue on your end. Let me continue with RedCraft, folks. And Adam, please, I'll try to monitor chat, but if you can bring it to my attention also.
I certainly will.
All right. So this is not where I want to go to. So RedCraft operates in two primary stages. We got stage 1 and stage 2. And RedCraft, also the unit of RedCraft's structural assembly, so RedCraft stands for Residual Dipolar Coupling Based Residue Assembly and Filtering Tool. So what we do, we treat fundamental units of a protein not as amino acids, but as peptide planes. I am aware that peptide planes and amino acids are slight shift of each other. So I'm going to treat the two interchangeably, but I am aware that they are not. And for the most part, this interchange between amino acid and peptide plane kind of can become non-issue. So I'm going to treat it interchangeably, but at some point you may have to pay really careful attention to the distinction between the two. RedCraft operates in two stages that I'm going to demonstrate, stage 1 and stage 2. And during stage 1, actually that's next one, so I'll tell you about it in the next slide. But RedCraft operates on the following 3 assumptions: that standard peptide geometries are not violated. This means, for example, your peptide plane is a peptide plane and there's not a severe violation. I must stress the term severe. Severe violation meaning that if omega angle varies between negative 170 by 10 degrees plus minus 10 degrees, basically, it's not a big deal, and the structure can be created by compensating for alteration of omega, stuff that are in the terms of phi and psi in the dihedral torsion angles. And you will see why in practice. And also the correct assignment of RDCs are in place. So if your data chemical shifts are misassigned, you're gonna see a problem in structure calculation, and also assumes that you do not have dynamics. Violation of any of the basic assumptions of RedCraft will be manifested in some sort of a hiccup in some sort of a thing that we call dynamic profile. You will be able to identify one of these violations are taking place, and you are able to then go back, examine each one of them as following Occam's principle. The first thing that you want to do is make sure that there is no cis-trans change of the conformation of, for example, prolines. Make sure that your data is correct, is not misassigned. This is probably something you do well ahead of time. And then once you eliminate this, it indicates presence of dynamics, which then you treat it differently. And if there's interest, we can designate another session to just study the dynamics of proteins, how to characterize it. But for now, let me start. So during the stage 1, our focus is just to look at 2 adjacent peptide planes and examine what is the optimal connectivity between 2 adjacent peptide planes, the orientation of which respect to each other are altered by just changing phi and psi. So in this particular image, what you have, each color represents an amino acid. Peptide planes are marked by peptide planes, and the orientation of peptide plane red and purple is going to be changed based on rotation of phi and psi that is centered around the C alpha of a particular residue. So RedCraft starts right off the bat by assuming assuming one of the following 3 sets of connectivity between peptide plane I and I+1, so two adjacent peptide planes. You have the freedom to start from an entire space spanning -180 to 180. In this case, we have snapped the grid search to 10-degree grid search, and you will see the 10-degree grid search. We overcome it by doing some sort of minimization, but also really doesn't make any sense. Plus minus 10 degrees is within error of structure calculation. You can from here go to a more stringent Ramachandran restriction that we call this Ramachandran level 2, that this particular set of permissible dihedrals are explored, or you can go to a very stringent, healthy looking structure that is confined to Ramachandran level 1. So you can start with any of those. And the very first thing that Redcraft does, it uses additional information if you have in order to refine the search space. So for example, NMR data, if you have 3 bond J couplings, you can then further refine it as to what are the permissible phi angles. So in this particular case, you start with ROM level 2 based on J couplings, you may be able to further refine it. Your refinement may be based on Talos, your refinement may be based on evolutionary search of PDB, which we have developed tools there. Or it can be based on secondary structure prediction. If you have some sort of a secondary structure prediction that says this region, this particular pair of amino acids should be in alpha helical formation, then you can just trim it down to just alpha helical formation. So whatever other filtering you want to implement, whether it's NMR-based data or whether other knowledge-based data, you can incorporate in here. And then Redcraft takes every single one of these combinations and creates the local geometry, evaluates that given small fragment for fitness to residual dipolar couplings, and then ranks everything on the order of best fit to worst fit. So in this particular instance, for example, it creates an angle of -30, -20 for phi and psi connecting these two the peptide planes, with the fitness to residual dipolar couplings of 0.4. And the next one is -60, 170, -50, 160, and so on and so forth, all the way to -170 to 120. This is what the result of the first stage is. I'm going to stop here and see if there are questions. Is it clear what stage 1 is doing? It's just looking at the data from residue I and I+1, and from there determines what are the most fit phi size between these two adjacent data points. Okay, so if all things are ideal in life, then of course this top entry -30, -20 would be the geometry connecting residue I, let's say residue 1 to residue 2. And then at that point, you can repeat this exercise between 2 and 3, and you can determine the angle between phi psi of residue 3, and then so on and so forth, and you would have your final structure. But of course, the problem becomes far more difficult than this. It's because of the localized availability and scope of the data. What is ranked to be ideal here may not be ideal in the global scope of the protein. So even though locally -30, -20 may be the right structure, optimal structure, but when you throw in data from the entire protein looking at the global structure, it turns out -50, -80, well, that's a bad example, and maybe -50, 160 is actually the true global optimal point. So from that point, and in fact, it turns out that almost never, when we are looking at experimental data or synthetic data with error added, you will never have the actual dihedral, the correct dihedral be on top. It's usually embedded within the top 50, 100. If your data is erroneous, it's going to be deeper. If your data is cleaner, it's going to be more shallow and superficial and on the surface of this list. So to overcome this global optimization issue, we deploy what's called essentially the second stage, stage 2. And this one, I'm just going to verbally describe what it does. And then as we go into the demonstration of the software, I can maybe expand on that a little bit more there. So what the second stage does, it starts from an initial dipeptide. So we have two peptide planes, and it appends the third peptide plane. It exhaustively looks to see what combination of first and second and third works best. From there, it evaluates an exhaustively large number of conformations, sometimes in excess of 100,000 conformations, ranks all the 100,000 conformations, and selects only the top n, where this n is the depth of search. Then it selects the top 1,000, for example, structures for further elongation by residue fourth, creates all the exhaustively combined combinatorial, exhaustively looks at all the formers, finds the top 1,000 and propagates those 1,000 forward for elongation by the fifth one, by the sixth one, and so far and so forth. So I know this part of it was a little bit mysterious, but I'm hoping I can clarify in the demonstration of the software. We have done that in a number of cases.
Home, sorry to interrupt.
Yes.
Would you mind a question on that?
Yes.
So where do you begin with that elongation step? Which two peptide planes are you starting with?
Right, so that's a good question. You want to start it with the place that you have the richest data. So you kind of want to look at your entire structure, your protein structure, and look to say, for example, residue 15 has the richest set of data. You want to start from there and work your way toward N terminus or C terminus of the protein. But in the things that I am showing right now, basically, I'm going to start at the beginning of the protein and work at the N terminus and work my way all the way to the C terminus. But the best successful approach is to start from where you have the highest data density.
Okay, and how much variation do you see if you don't start at that optimal location?
Not a whole lot. So
Okay.
in the stuff that I will show you, you will see that it just doesn't matter. The question always is, how far can you push Redcraft with sparsity of data? And you will see I'm going to start with generous 6 RDCs per residue. And as part of demonstration, synthetic RDCs, as part of demonstration, I'm going to show you, I hope to have time to show you experimental data with only 2, NH, C alpha, H alpha. And of course, when you get NH, C alpha, H alpha, there are residues such as proline that you may not have those. And in fact, it turns out you may have protein, and glycine, for example, in a sequence where you may not have NH or you may not have C alpha, H alpha. So then there's this gap of data. And you can still tinker with some parameters of Redcraft to walk through it. But at that point, when it becomes really sparse data with huge gaps of data, then the question is, what do you do? And I'm hoping that will be part of the discussion. We have highlighted some of those in our publication. So if there are things we don't get to today, reach out to me. I'm happy to do this on individual basis, or I'm happy to point you to a particular publication where it discusses that, whatever question you may have. So going forward, we have done it on a number of cases. In a more recent publication, we are trying to get it out. So if you are serving as one of the reviewers, keep an eye open. What we have demonstrated is that compared to the previous reported structure calculations of these proteins with residual dipolar couplings, we use only 22% of it, and we managed to get a structure that is, fairly close. This is without minimization in Explore and IH. This is just raw structure that comes out. So as little as 11% of the data. And we have extended structure calculation to larger proteins, but this is with synthetic data because experimental data do not exist here. So if you just calculate structures adhering to only 10-degree increments, not worrying about omega angle refinement, you can go as high as 570 residue protein and get structures fairly accurately. And from there, of course, you can use any of these to put them in Explore and IH or any of the other refinement strategies and further refine the structure. I have in here, you can look at it later if you like, the number of kinds of RDCs that we can use in order to calculate structures. It may be limited to only NH from 3 alignment media. It may be collection of RDCs that can be collected from deuterated proteins. I'm not going to focus on these too much, and I'm not going to focus, essentially, I'm just going to jump to the demonstration. I'm kind of eager to do that. If you guys have questions, let me know. If not, I'm just going to start with the demonstration.
I have a question about the combination
Yes.
approach of NOEs and RDCs. If you provide Redcraft with a structure that was computed first with NOEs, will it use the assumptions that it's making to correct any angles that are considered violation?
So the way that normally we approach situations like that, let's say you have a proposed structure as a starting point. And because Redcraft operates in rotamer space, what you need to do, you need to translate that structure into phi size. Then at that point, from your original structure, you create the starting point of dihedrals that connect residue 1 to 2, 2 to 3, 3 to 4, and so on and so forth. And we have scripts that will do this. And you can add in there uncertainties that you experience, you suspect, at each location. So if you're fairly certain, for example, a region is going to be alpha helical, and you know already a starting point for phi size, then you create the appropriate angle for that particular residue to be around your alpha helices and maybe allow plus minus 5-degree variation between your proposed dihedral. And as you go through the loops, then loops may be points of ambiguity in your structure, or maybe there are some other regions that are ambiguous. Then you can expand the search parameters for that particular residue to include plus minus 30 degrees, 40 degrees, 50 degrees, however you want to do this, and allow that to be the starting point of Redcraft. So Redcraft then operates in the rotamer space that has been defined by the user based on some initial structure and knowledge. So I'm kind of giving you a high-level answer, and I'm not sure if this makes any sense to you.
Yeah, that's brilliant. Thank you.
So if you start with a structure and you essentially convert your structure to, I envision Talos, where, for example, what you get out of it, residue 1 is 5 side dihedrals of minus 60, minus 40, and variation of plus minus 20 degrees. You take that, you convert that to a list of angles that connects residue 1 and 2. And so on and so forth, and then you let Redcraft do its thing with residual dipolar couplings. And it works reasonably well.